Welcome to Lecture Online, and now that we have a basic understanding of what normality is, let's do a few examples to enhance our understanding, so to speak. So, again, the official way of thinking about normality is it's the number of equivalents of an oxidizing agent or reducing agent per liter of solution. Again, the equivalent simply means the number of moles of electrons being transferred, either donated or accepted. And so a better way of thinking about normality is simply that it's the number of moles of electrons transferred times the molarity of the solution. But it depends where we place that solution, because if we, for example, place 0.5 molar solution of potassium permanganate in an acidic solution, you get a different normality than when you place it in a neutral solution or a basic solution. And so let's see what the normality would be in each of the three cases. You have to keep in mind, though, that when you put the potassium permanganate in solution like that, it will dissociate. You'll get the permanganate ion, so you end up with the manganese and the oxygen like that. So remember that this is a +7 state and a -4 state coming from potassium permanganate. And in a acidic solution, so in solution number 1, which is the acidic solution, it will go to just the manganese ion at a 2+ state, and so the difference in the electron, or the what we call the oxidation state, or the oxidation number, is a difference of 5. So that means that for every mole of potassium permanganate that is placed in acidic solution, you get the number of moles of electrons transferred will be 5, and so therefore the normality will be 5 times the molarity. In this case, the molarity is 0.5. In this case, that would be equal to 5 times 0.5, n, which is equal to 2.5 normality. So the normality in acidic solution will be 2.5 for this particular instance. Now, in a neutral solution, what happens with the permanganate ion, starting at a +7, instead of going to a +2 state, it's going to go to a manganese oxygen 2. And so what happens here is that this is a -4, and then this would be a +4. And so you can see that the change here is only 3 moles of electrons per mole of potassium permanganate. And so therefore n will be equal to 3 times m. In this case, that would be 3 times 0.5, or n, because we have to use the units of normality. N, which is equal to, I'm running out of room here, 1.5 normality. And then what happens when you put the ion in that would be from a +7 state, and of course that would be 4, that would be a minus, so that would be a minus, that would be minus, and that goes into what we call manganese O4. Let's see here, that would be a -2, that would be a +6. Okay, that's what it is, that's right. So we go from a +7 to a +6 oxidation number. So therefore the normality in this case is equal to 1 times the molarity. So in this case that would be 1 times 0.5 molar. And so that would be equal to 0.5 normality. So really notice how it makes a difference where the ions are placed. If it's an acidic solution, in this case, there's many more electrons transferred, so the normality would be much higher in an acidic solution compared to a neutral solution compared to a basic solution. All right, but if you are given the normality, that's already taken into account. So let's do another example here. Let's say that we're asked to find how many milliliters of a 2 normality potassium permanganate solution are needed to oxidize 50 milliliters of 5 normality of iron sulfate. It doesn't matter what the solution is, because you're already given the normality, which takes that into account. And so what we have to do then is simply keep track of the number of electrons transferred times the volume of the solution. So what happens then is we simply then multiply the what we call the normality times the volume of the first solution, and that has to equal the normality times the volume of the final solution, or the second solution in this case. And so here, since we're looking for how many milliliters of the 2 mole of 2 normality of potassium permanganate, so let's say that's our first item, and this is our second item right here. So what we're looking for is, we're looking for how many milliliters, we're looking for this volume right here. All right, so then we simply solve for that volume. We can then say that volume is equal to the normality of the other solution times its volume divided by the normality of the first solution right there. So in this case, the normality here would be 5. The volume would be 50 milliliters. And the normality of the oxidizer here, that would be 2. And 5 divided by 2 is 2.5. 2.5 times 50 is 125 milliliters. So you can see that normality is actually a really handy unit when we're doing oxidation-reduction reactions, because in that case, we're already taking into account that it's not just the number of moles in the solution, but also how many electrons are being transferred per mole. That's already taken care of by writing the normality. Also, by writing the normality, you already take care of the fact that you are placing it in a particular solution, and the normality is already taking care of that as well. So all you have to do is simply come up with that simple equation, find what your unknown is, solve for the unknown, plug in the numbers, and there you have the number of milliliters of solution of potassium permanganate you need to oxidize 5 normality of 50 milliliters of iron sulfate. And that's how you do that.